So I thought I'd like to talk about this now before I get assimilated and sort of don't remember anymore why I was here. And I think it's already starting to happening. So it seems to me that there are at least two motivations. I should have many more, but let's just name two for homotopy type theory. The first one is to exploit the homotopy interpretation of type theory. Of type theory to sort of formalize, to do a formal development about homotopy theory, to reflect homotopy theory, to formally develop homotopy theory. Okay. And I think it's quite interesting, and there's lots of success stories already. I mean, there is also some interest in how homotopical concepts are modeled in type theory. So these higher inductive types, I think, are quite fascinating. Then I wanted to give another motivation that homotopy theory is a sort of canonical extension of intensional type theory necessary for abstract reasoning. And it can be motivated without any reference to homotopy theory. So it stands on its own. And so obviously I want to talk about the second explanation, or second view. I think that intensional type theory is usually viewed as a very, and the name says, it's intentional approach to mathematics. Very lots of emphasis on detail, and hence in some way unsuitable to do abstract mathematics because you are just too much concerned with detail. This is maybe related to this suggestion that type theory is very, very formal. However, I think actually the contrary is true, namely that intensional type theory is ideally suited for doing abstract mathematics. It needs to be extended, and homotopy type theory is like the extension we need, which is necessary. It is actually, in a sense, more extensional than classical set theory. And it's also more extensional than what's called extensional type theory. So indeed, extensional type theory cannot be made extensional in the appropriate sense. Okay. Sorry? No, I wanted to stop now. Okay, a little bit. Okay, so let's first look at. So what I want to use, I want to introduce the principle of extensionality, and I want to argue that this is valid in some sense for homotopy type theory, but fails for any of the others. Okay. So let's start with functional extensionality. This is a simple example. Let's consider two functions f and g from nut to nut. So just to be concrete, lambda x is x plus 0, And G is lambda x 0 plus x. Okay, how does this work here? So these two functions, we can in intensional type theory, we can show that there is what do I want to say first? Yeah, there is no proof that f is equal to g. So how can we see this? This is actually a consequence of the equality reflection property. Namely that in the empty context, we can prove that two terms are equal. And now I'm talking about terms because I'm doing meta theory here. The two terms are equal if and only if they are actually convertible. And that's very easy to prove. It's a consequence of the normalization theorem because the only proof, the only canonical proof that T equals U is reflexivity. And if you prove this using reflexivity, then the two terms T and U must be convertible. I mean, this shows that this inductive, the so-called inductive definition of equality forces us to identify propositional equality and definitional equality in the empty context, which is maybe something we or very likely something we don't want to have. Any type, actually, sorry, yeah. Of any type. It's not
In general, then your argument was by induction, because you just argued perfectly zero.
No, in this okay. What the argument is that the only canonical proof that T is equal to U is reflexivity. Yeah, the canonical element of equality proof. In the empty context, any term should be reducible to a canonical term.
Simple counting would suffice. If you have a model of type theory where f and g are equal, you also have that. But that is, of course, a nicer way.
Yeah.
The way you do it is very nice. But the simple counting model would suffice for the outlook rate of f equals g.
Yeah. Yes. Yes, that's hard to see. It's very intentional.
They are different computations. They have different codes.
I mean, I also assume implicitly that it's clear that these two terms are not convertible, because for them to be convertible, x plus 0 has to be convertible to 0 plus x. And I mean, depending how we define equality, one of them is convertible to x, but in the normal definition of, or in the definitions of addition we can do, x plus 0 is not convertible to 0 plus x, or at least not with the standard definition, any of the standard definition of addition. Okay, so we cannot prove that they're equal, but there are no properties which distinguish f and g. So what and we can prove this using the Satoid model, but I don't want to go into the details. First of all, it's not exactly true if I write it this, because obviously there is a property which distinguishes f and g, namely being equal to f. I mean, I could just write, yes, p of f, or p of h, is equal to f, yeah? And obviously that's a property which distinguishes f and g. It's a bit circular, yeah? Yeah, maybe. But the problem here is I'm using equality, and so I'm getting a bit circular because I wanted to talk about the property of equality, and now I'm using equality as a property to distinguish these two elements. So that's maybe precise, which are not using propositional equality. Okay. And there are no properties which distinguish f and g which are not using propositional equality. So if you have, yeah?
What do you mean by distinguish?
I'm looking for a predicate, say to prop, whatever this means, yeah, such that PF is inhabited and P of G is not. Okay? Yeah, metastatic. P is in the empty context. Okay.
And the system is restricted in some way. We have about universes or something. Then if I have some universes and I use them
Mm-hmm.
to find something that acts like equality, can I restrict on?
You mean Leibniz equality? Yeah.
So there would be a restriction on what types are available.
I guess so.
Is this a claim or is this empirical evidence? Or did you say there are no properties which distinguish f, which are not using equality? What is the status of that
Mm-hmm.
sentence?
You have a meta-theoretical proof using principle equality.
Yes, setting models, but not using universes. That's a good point. Yeah. So yeah, I have to think more about this universe issue. And so I want to claim or state this principle of extensionality, which is broken with this, because I have two objects which I cannot distinguish, and I cannot prove equal, and that's something which I think is this fundamental incompleteness of a theory. So, principle of extensionality. Ooh. Now, the principle of extensionality I would apply to any sort of extension of ITT or any variation of type theory. So it's a theory potentially extending ITT or doing something new. So principle of extensionality, let me first give a slightly too powerful statement. Given two objects, A, B, of A, we can either prove them equal or find a property which them. So I hasten to add, I don't want to say that equality should be decided, also this or here, we really have to read classical. So what I'm saying, I don't want to have two objects which are both not provable equal and indistinguishable without using equality or propositional equality. Yeah, it's a good point, which I haven't really thought about, that equality sneaks in via this impredicative higher level encoding. So that's the weakness of what I'm saying so far. Yeah.
There's a question regarding this here. Where in your proof here, where you said higher probability
Mm-hmm. Basically, I start with a type theory without propositional equality. Yeah. And now I say, okay, let's construct two objects. And now, now I'm adding equality. So there are two objects. So either I find a property which distinguishes them, or I should be able, in my now introduced equality, to prove them equal. Okay. Mm-hmm. So you can
So even if you get this principle of equality, you will have equality here, and you'll be able to say equality false or not.
Sorry? You will?
You'll be able to say equality false or not.
Yeah. I will.
So you, even you just said that you can prove it internally. That's the meta theory.
Yes.
It's a meta theory.
Yes. So this is supposed to be a meta theorem. Yeah. Yeah. Okay.
Also, is this statement itself being taken as a kind of principle or an academic theorem? Because if there's an academic theorem, it seems to suggest something like a
Yes. So I say I would use a negative form. So as a meta theorem, I don't want to have two objects which I cannot distinguish and without using equality, and I have to add something to outlaw encodings or reflections of equality using higher order definitions. So I haven't really thought about this, but that's the idea. Yeah, that we restrict ourselves in our property, so we cannot really talk about equality, and then we introduce an equality, and this equality should just correspond. So what's the idea? So the idea here is that we want only to talk about what we can see from outside. I mean, so how can we make precise what we can see outside? I mean, these are properties which don't use explicit intensional concepts like intensional equality. So so I can not distinguish them, so like these functions. And I should actually it's not an accident that I cannot distinguish two extensional equivalent functions. But actually, this is a consequence of our view what is a function, of the constructive view of a function. Namely, that if I give you a function, the only thing that you can do with it is applying it to an argument, and that's quite intended. So we could have another notion of a function, which what one could call a function code, and you could inspect a function code and see, I mean, how the function is realized. This is what you suggested, these codes of functions. But this is not a good, this is not the concept of function we want to use, and it's not a very stable concept, because each time when we talk about our function, we really talk about all the encodings, and as soon as we add something to our system, as soon as we add a new principle to compute, the set of function or the collection of function is going to change. So it's almost impossible in this context to prove something general about all functions. A function in this case is not an abstract concept. Yeah.
I thought what was happening is the two objects are, in some sense, depending. Their equality depends on
So that the,
Traditional is always
okay. So maybe I should make clear that this is an attempted approximation of this principle, and Steve had already found one weakness that you can include equality with universes, and you identify another one that I make a possible recursion theoretic statement, which requires a very strong semantically complete theory, and neither of them I want to do actually. So maybe I should write first approximation of, okay. Okay, and these two issues have to be taken into account. Yeah. Kill it again.
Potential problem here.
Yeah.
Point out another issue. It's often the case in free algebra that things will be different, not because they behave differently in the algebra, but because they admit interpretations in something else than intended.
Yes.
So we have a situation like that here maybe where the system itself doesn't allow you to prove A and B equal, but it also doesn't allow you to define enough properties
Yes.
in the system to distinguish them, because it's a very maybe conservative system. It doesn't allow you to define so many properties. But you may be able to interpret the system in a much richer one, where there are such properties which could distinguish them. And that's why you don't want to prove them equal either, because that would rule out such
Such an
interpretation.
extension, yeah.
So you could have extensions of the system, if you like, or semantic interpretations, where these things are different. They're simply not, the difference is not definable in the system itself. And that's why you may have neither a property, definable property that distinguishes them, nor a proof that they're equal. And that's a perfectly reasonable situation to have them, if you're thinking about the system as a kind of like a free type thing which could be interpreted or mapped into other symbols.
Yeah. So that requires more thought, what we really mean by this. Okay, what I wanted to point out is that functions we view, and this is important for our understanding of function, that we view a function as something which is in a black box. So that means we cannot look inside. And I mean, I think that's similar to digital rights management. When you buy a piece of music, you're not allowed to look at the bits. Yeah? And by analogy, functions are similar. There's a contract that if I give you a function, you're not allowed to disassemble it. And hence, any two functions which play, or any two pieces of music which play the same music, we would mathematically consider as the same objects, because we are not able or we're not allowed to look inside to see how it's encoded. Okay, so that's function extensionality. So, okay, so how can we fix this? The fix is well known. I mean, and I've discussed it here, that we, for all xa, f of x equals g of x, and we have here f equals g. So we know that there is one proof in this direction, which is called for Kong up. I don't know. I don't know, maybe there's a up. Just up. So, how would you call this? Up 1 0. Okay. Yeah, because we just have to prove it for the reflexive case, and then it's just by lambda x raffle everywhere. And in the other case, we introduce x. And how is this justified? Because we want to identify the reasons that two functions are equal with the reasons that they are pointwise equal. And to identify this, we need actually to make these inverses. But we could go further. I mean, or a slightly different view would be simply to say that f equals g is defined as, for all x, a, fx equals g of x. And that seems to be quite natural, because in a way I would say maybe we shouldn't start with an equality, especially since this inductive equality has got these properties that really reflects definitional equality, which is something we don't want. But instead, we define equality. So we define equality for every type in a sensible way. And clearly for base types like natural numbers, we have a easily accessible definition, which is just a recursive definition. And for other types, like here for function types, we define equality to be the extensional equality, which corresponds to them being indistinguishable. Yeah.
In that case, the equal sign is never identity.
No, what I'm saying is identity types shouldn't be, should be introduced, but they shouldn't be introduced by reflecting definitional equality, but they should be introduced for every type and motivated by this idea of extensionality. So there should be equate these objects which we cannot distinguish using other properties. Okay. So the question is now, can we recover the usual properties of equality? Also, are we justified to call these defined equality? And so, for example, can we prove them to be reflexive? And can we prove what's called path induction? Can we prove the eliminator? So in this particular case, this is possible as long as we restrict ourselves to type 0, to sets. Then we can derive equality elimination for this type. And basically all we need here is to prove the transport. Transport we can prove recursively. This is also something which comes out of the setoid model. So in this particular case, for type 0, for 0 types, we can justify. So justify that this is an equality. Okay. Yes, yes. We just use X. Sorry? It's a 0 type. Yeah, yeah. As a decidable equality, and hence any two equality proofs are equal. Okay, let's move to univalence. So the notion of extensional equality becomes important when we talk about infinite objects. So like functions are infinite objects. And for infinite objects, it seems to be fundamentally wrong to identify the object with this description, because there's more than one possible description of what we would view as the same object, and which mathematically, from an abstract point of view, should be viewed as the same object. But functions are not the only infinite objects. If you look in type theory, the other kind of infinite, or one other kind of infinite objects are types. Yeah? So the question is, when are two types? So let's say A, B in some universe U are equal. Well, then two types are two types equal. And we can just, for concreteness, have a similar situation. We say A is a type of natural numbers, and B is a type of lists over the unit type. Just as the type is one element. And the situation is very similar to the situation with extensionality, with functional extensionality. Namely, we cannot prove that A equals B. So the reasoning is the same, because if there would be a proof, then it would be, in the empty context, there has to be a proof of reflexivity, and obviously reflexivity, they're not identical. On yeah, that's another example. Yeah. Okay. However, I'm not 100% sure how to prove this. I think it can be done using the groupoid model, but I just say like conjecture there is no property which distinguishes A and B without using propositional equality, or I mean intensional equality. So I think that can be shown with the groupoid model, but I haven't checked the details. If it's, but I mean, you can try, and certainly empirically, that seems to be the case. Obviously, if these two types are not isomorphic, then it seems obvious to be possible to come up with a property to distinguish them. And again, this is no accident, and that's actually a different from set theory. Yeah, I mean in set, yeah. Yeah, that's true. Good point. Yeah, we have to use extensional equality further down. Yeah. We have to encode the whole. We have to really bring it down to some definable property which doesn't use equality. Yeah. So these are both inductive types. Yeah, they have a very similar definition, but using, let's say, different names for the constructor. I mean, here nil and const. So they are intentionally different, but they're not really very different. So one could have a system where actually these are actually. Your example with binary and unary. Oh yeah. I think your example with the binary and unary encoding is more is better in a way, because then one really sees the difference in the definition. Yeah, so that's true. For example, yeah, on this level. Yeah. This is also a question. This is a bit now has to do with the concrete encoding. Yeah, whether we have an encoding where the constructor names matter, or maybe have an encoding which is more abstract, where the constructor names don't matter. I mean, depending on your choice of encoding, you can have a little bit more extensionality. So there's always an example which falls outside. We never really capture extensional equality, but we can be a bit more extensional. But it's very unlikely that our equality captures something like binary natural numbers and unary natural numbers. Or let's see, here nut and here binary trees. Okay. These are clearly intentionally different types, but they are not distinguishable. So you cannot write a property in type theory distinguishes trees in natural numbers. And I would say this is not a coincidence. It's different to set theory, because in set theory we can distinguish isomorphic sets. Yeah? We just have to talk about the elements. Maybe one has an element which the other one hasn't. And this is a fundamental difference in type theory. In type theory, I would not think of types as like sets, which are basically sorting the elements which are already there. But types in type theory mean, in my understanding, is that the elements are only created once we know the type. So we cannot really talk about an element in isolation of its type. So elements and types always go together. And hence, as a consequence, we cannot really talk something which only has to do with like having a different encoding of the same type, because then we would really to talk about the intensional property of the type. If we can only view extensional properties of types, then all what we can see is stable under isomorphism. So again, like for the functions, it's not an accident that we have no distinguishing properties, but it's actually there by design or by our understanding what is a type. So we can fix this. I mean, again, it's, I would say, invalidates this principle of extensionality in its final approximation, hopefully. And we can fix it, and the fix is well known, by saying, okay, two types are isomorphic. Let me just write down what I mean by isomorphism. So I mean there are two functions. This is the usual definition, and then there are two proofs. And I guess maybe I should turn one around, but I don't. So that's what I mean by isomorphism, and here is equality. And again, it's easy to prove that we have a proof in this direction, which is basically a consequence of the fact that isomorphism is reflexive. That's because we only have to prove it using path induction for A equals A, and then to prove that A is isomorphic to A. So it's called isomorphism. But the other way, I would call univalence 0, because it's univalence for 0 types, so assuming that A and B are sets. And then this fixes this problem, because isomorphism precisely characterizes this extensional inequality between types. However, there is a little snag here, which I think is well known. Namely, in the moment when I introduce this equality or introduce this principle, or alternatively, I say that A equal B simply is defined as A isomorphic to B. In the moment when I do this, I lose another principle, namely I lose the principle of uniqueness of identity types. And I mean, this is quite easy to see, because equality isomorphism on bool, so as bool equal bool, certainly has got two different elements, and if I identify equality with isomorphism, I get two different proofs to prove that bool equals bool, and hence I have to give up the principle uniqueness of equality proofs. But however, the definition of isomorphism, I would say, already implicitly assumes that these A and B are 0 types, because it doesn't really talk about what happens with alpha and beta. And in the moment when I give up uniqueness of equality proof, I have to add some further coherence properties. And if I don't do this, actually, then this identification becomes unsound. And so I think you have seen this already, what you have to add, let's call it phi. So what I'm saying is if I apply f here, or I write f equal, so for the equality effect of f to alpha a, then that should be the same as beta of fa. And because here, in this case, I have two different ways to prove this equality, that fgfa equals fa, either with alpha or beta, and so I better identify them, because all the proofs I get out of this direction here do have this property. Another possible property would be to do the dual statement, which is g equal, so I let out the quantification, beta b equals alpha of gb, and that's the other triangle equality if you do this as an adjunction. Now, luckily, these two are themselves isomorphic. So I can identify them. That means I only need one. And I can choose which one. It doesn't really matter, because the other one is their equivalent properties. And that means, okay, so I move to this refined notion of isomorphism, of coherent isomorphism, or adjoint isomorphism, and that's then the correct notion. And in a way, I always think this is quite lucky, because it could have happened that we had an infinite sequence of coherence properties, but it seems that we don't need them. Okay. Yeah, but this is also now my argument why extensional type theory cannot be extensional, right? Because extensional type theory identifies provable equality. So if you have if you have a proof that A equals B, then that is interderivable with A and B are definitionally equal. And now if you have any proof, we can replace any proof by reflexivity. So in a way, in extensional type theory, uniqueness of identity proofs is already built in. We may not be able to prove it, but we cannot actually distinguish equality proofs, because we can replace any equality proof by reflexivity. And hence, we cannot actually identify equality of types with isomorphism, because isomorphism is clearly, they're clearly different elements. So in this sense, I would say extensional type theory cannot capture extensional equality of types. So both set theory and extensional type theory fail this extensionality principle, while homotopy type theory, so intensional type theory, which supports this identification, then satisfies the principle of, or hopefully, that's another conjecture, satisfies this principle of extensionality. Okay, so what should be done, or what remains to be done? Or didn't? What? So I would say I would like to have HTT formulated in a way where equality is defined extensionally. So equality is defined to be this extensional equality. So equality of functions is just this pointwise equality, and if equality of types is this coherent isomorphism. And okay, equality of sigma types we know, equality of natural numbers I think we know as well, or of W types. That shouldn't be an issue. So now we have a type theory which has some notion of equality, and the question is, can we now recover, so define equality by recursion on types? So equality, and this is extensional equality. It's the equality we mean, which corresponds to the idea that we can only see objects from outside and we cannot look inside. So that should be the right equality for any type. And now is recover the usual reasoning principles. So that's, as particular, we want to show it's reflexive, that the path induction, or J, holds, and that a certain equality holds, in particular, that the equality J beta. So if I apply the path induction to reflexivity, then it should give rise to the identity. So one word here is, so J beta is a definitional equality in intensional type theory, but I don't think that's necessarily the case. I mean, a J beta may well be a propositional equality, and that should be sufficient. So there are, so how can we achieve this? So I have already indicated that this can be done by internalizing certain models. So for extensional equality, it was a Setoid model, and we can go a bit further, I think, using the groupoid model. But if we want to go all the way up, we need something more powerful, like using an omega groupoid interpretation of type theory. So the equalities we want, the ones we get, or in this omega groupoid interpretation, we have to show that we can interpret equality types. Yeah? That we can actually interpret equality types together with J and J beta in a sound way. And I mean, I think there's people already working on this, and it may be possible, and this is, I think, what Thierry looks at, is using this sort of classical idea, instead of using omega groupoid, using Kahn complexes, and do it this way. But we have to be able to do this internally in type theory, and there seems to be, that's something which is still open. All I wanted to say, this is my view, is that I would start with a definition of equality, or interpretation of equality, and then recover the principles of equality around